So we learn how to integrate stuff using different methods. There's so much more than what we learn in this class by now. But we learn integration by parts, use substitution. We learn integrating fractions using partial fraction decomposition, integrating tricks, integrating using tricks. Now integrating using prepared tables. But what if nothing is working? What do you think you should do if nothing is working? So you have integral and nothing is working. What do you think you should do? Guess. What if like you have salary, 6-digit salary, and part of your job is to solve that integral and you do not find how to do it? Would you just ditch it and then quit your job? So what would you do? What will be like, honestly, imagine yourself in a situation. You don't know how to do the integral. What would you do? Wolfram alpha. Actually, it's not a bad idea, which goes into a bigger question. What if it's not Wolfram alpha? Then it's a computer. And computer takes us to numerical integration. 6.5. 6.5 uses numerical integration, which means we will try to use technology to approximate the integral. And that is unfortunate. If we approximate an integral, we're not going to get the exact answer anymore. But it's better than nothing. So finally getting to this last step of integrating, which is approximating and getting at least what we can get. Numerical integration. Check this out. We will have several methods in this class, but there's so many more than that. So we will have, for example, the integral of this impossible function. Well, function is possible, but there is no straightforward way to integrate it. Those are the functions that cannot be integrated. Check this out. Graphically represent three, you don't have to copy this, three definite integrals that cannot be evaluated using anything. No exact answer exists in our class for these three. E to the minus x squared, sounds so simple. Sine x cubed, sine x over x. Sine x over x, what hard was that? Somehow, you see, you cannot do it. So what we decide to do is to use your favorite Riemann sums. Yay. Thank you. Finally, someone supported my yay. F of x dx equals, well, let's do equals. Let's do use Riemann sums. If you don't remember what it is, I'll remind you. But it was like somewhere very far in your past life we learned Riemann sums with double N. Sums to approximate AP. We usually put APP, approximate, but for the first time I'll write it down. Approximate the value. So that's what we're gonna do. Riemann sums, those like huge sums, we learn. Oh, come on, it was so pretty. Bless you. So we're gonna be using these beautiful sums, which we learned in Calculus 1 when we were learning how to integrate in general. Let me show you some notation again, which actually we had before. So don't copy this yet too, I will show you later what we need. Let xi be a plus I times delta x. That's what we did in Calculus 1. And I'll explain you what it is. I is a counter. That's what you use in computer science a lot. I, J, K, N are usually counters. This counter is running from 0 to n. We're going to do that more in other chapters with series and convergence. So we're going to choose. This is my choice for now. And then we have here starting point and a step size. And I will show you that in a second. So delta x. What is delta x? That is b minus a over n. That is basically the width of each rectangle. Welcome back to Calculus 1 class. That's the review. Maybe you missed it, so. Widths, not lengths. Widths, let me know if you don't see the green color. Widths of each rectangle. B minus a over n. So the whole interval divided by the number of rectangles we want. And then we had three cases, if you remember. We had three. Let me move this. Oh yeah, I have lots of cool animations to show. That's pretty cool. We had 3 cases, remember? We had left endpoint, right endpoint, and midpoint. We're kind of going back again to that topic, but we will go to something more interesting as well. So there were 3 cases. What did I just erase? Left endpoint was called L sub n. That is not an international notation, but usually it is L sub n, where n is number of intervals. Left endpoint method, endpoint method. And it means it's something like so. Again, it's calculus 1 material, so you don't have to recreate this. We're just reviewing why it's important, you will see. When you have this impossible area, which is this one, you can try to just basically cover it up with the objects you know, and then the objects you know, for example, is rectangle. Look at my cute phone case. So rectangles are very nice shapes. They can cover up some kind of approximate this screen. And I can say, oh, this is like approximately 25.3 cases. And then I just measure this case, which is width times length. That's a common idea for human being nature, to calculate something we don't know with something we know. It totally makes sense. So let's cover it up with rectangles, but being consistent about it. If we choose left endpoint, well, let's do that. We're going to start with left. Again, don't have to review that, just reminding you. Touching the function with left endpoints everywhere. And then just keep going, keep going. This will give you either underestimation or overestimation. If you see lots of things being missed out, that's underestimation. If lots of things are too many gaps, that's overestimation. This is how it looks like. Touching the graph with the left endpoint, L sub n. And then n is how many we use. The more the better. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 or 10. The more the better, because if they get thinner, they definitely cover everything better. And an infinity of them will give you an exact integral. Right endpoint, R sub n. Right endpoint methods, endpoint. Same thing, but we're touching the function. Compare sine of x cubed. Now it's touching everything using right endpoint. And then the complicated one was midpoint. That one was not complicated from theory point of view. It's the same thing. Let's just touch everything with the midpoint. But calculation was annoying. So it's called M sub n. Here are 3 of them. Midpoint, midpoint, or middle point. People do not agree how to call it. Midpoint methods. So either touching with right endpoint, left endpoint, or maybe just do it with midpoint, like so. Calculating midpoint was annoying. That's why it's not a favorite method. We're going to review this a little bit in the your homework, but most idea is to go to the new methods. So I just told you, this is right endpoint. I just told you that it's natural for human beings to use objects we know to calculate something we don't know. So why rectangles? We were bothering you guys in calculus 1 with rectangles. Why not something else? Yes. What else we should use? So especially engineers and physics majors, I think, should be creative. And the computer sciences maybe saw a YouTube video about something like that, about how computer games are being created. They're using another shape, not a rectangle. So, trapezoids. Did you want to say trapezoids too? Yeah. Trapezoids. Do you remember what trapezoids are? Those are rectangles, but they are tilted at some kind of way. And this might cover those ugly, or not, I wouldn't call them ugly, they're actually pretty. But they will cover those tiltedness, you know, and that might make it better. The idea is to have less gaps. Because again, it will be approximation. We cannot create exact integral here. We can create it, but we cannot solve it. Exact integral was created. Here it is, integral of this dx. But now what? So we're trying to make it as good as possible to figure out the approximate area. So trapezoid is used. Look how beautiful it is. Those are trapezoids. So okay, draw this picture now because that is actually important. Not only we're covering this area with trapezoids, which will have barely any gap. Look at this. If the shape is not very, doesn't have cusps or sharp angles, trapezoids look really good here. No, not many sudden turns and stuff. And then we know area of trapezoid. People in this class, I don't. Well, just ask your phone. I mean, when I was learning this, I had to take a bus 1 hour away from the library, go there, check in, grab the book, check the area of trapezoid, check the book back, take the bus home, and then continue with my homework. You guys can grab your phone and say, okay, Google, what is the area of trapezoid? So I used to teach this in Zoom in 2020, and then I would say that, and people in Zoom, all their phones will get activated for Google, and then I would say, Alex, what is the area of trapezoid? And the other half of the class will get activated, so it was very fun. So lucky you, because for me it was a big struggle. So area of trapezoid is a plus b over 2 times the height. Well, in this case it's width, whatever you call it. Depends how it's lying down or standing. But basically 2 parallel sides are added, divided by half, and then multiplied by height. So let me show you something pretty cool, something pretty awesome. Come on, just do something. Seriously? Seriously? That's like the most inconvenient moment to do it. Maybe this one. Okay, good. Well, I'm gonna push through my phone. This is what they mean. Check out those beautiful trapezoids. Look how nice they're working with curves. Unlike rectangles, who do not work with curves so much because they are rectangles. It makes sense. Okay, it's glitching. So this is pretty cool. And the more the better, that was my point to show you. And then this one. Oh, look how they start. The more the better. It first kind of not, I think it's the same. See how it starts with 2, 3, 4, and then the more you do, the better it gets. So if your computer can handle 25 thousandths of trapezoids, then it will be a very good solution. That's the point. And computer can. So in your homework, we will ask you to do 5 or 4, and you will hate it. For computer, 25 thousandths probably is not a big deal. Depends on the problem. So that's what I wanted to show. Now let's actually do it. Let's see. Yes. What I wanted to now to show you is the formula. Trapezoid rule has a formula, and you will use that. Trapezoid rule. So they do not agree in English somehow. Is it trapezoidal rule or trapezoid rule? You will see both. Trapezoid rule. It has a formula. T, and it just collapsed it. Going. T sub n equals. Rude. T sub n equals delta x over 2. Delta x is my step size. Delta x is b minus a over n. And then you have f x sub 0 plus 2 f x sub 1 plus plus 2 f x n minus 1 plus f x sub n. Maybe increase a little bit. Sub n. That is trapezoid or trapezoidal rule. Put this in the table. I'll put it in the rainbow box. So this is what you will have to remember for the test. Right now it looks very sketchy. How can you memorize that? But actually you can just memorize the idea. The idea is everything between the edges is doubled. The outsiders are not. They're multiplied by 1. And then the step size, which is delta x, is divided by 2. So delta x is your step size. It's always like this because delta x is b minus a over n. So it's how thick or how wide the trapezoid, each trapezoid is. And then this is the way I memorize it. Why it's doubled in the middle. Check it out. The edges have one unique side, left side and right side. This is what these guys are. F sub 0, fx sub 0, and fx sub n. But then the sides in between are used twice. somehow this side over here is like a door which is shared by 2 rooms. So because this door is shared twice, we multiply it by 2, kind of. That's kind of intuitive way to explain it. There is a proof how the formula was created, and you can check it out as well. Now, how about other methods? What do you think about that? What do you think? What else we can use to find the area? Just make some guess. It doesn't have to be good. Anything is interesting. Like, what else would you choose? Can I, like, take a water bottle? Well, in 3D, we're going to be teaching you in Calculus 3 how to do volumes. Can we use water bottles, just fill it up? Say, what's the volume of the awkward shaped box? I'll just put lots of water bottles and see more or less it will fill it up. Then I will say, oh, the volume of this water bottle is no. But kind of not easy to find the volume of this. So what else do you think? Markers. I can fill up the box or any object with markers and then calculate the volume of this and say, it's approximately 57 markers. Triangles. What?
Triangles.
Triangles. That is a pretty awesome idea with triangles, which we're not going to cover in this class because it's time consuming. Triangles, for you to know, is used for computer games, and I'll show you next class on Friday. They are easy shape to manipulate because triangles can be stretched when you pull them away by edges. So actually computer games, if you ever go into the computer game engineering, then you will see lots of triangles. You will have to work with it. All the trees and stuff in computer games are done with triangles. Very cool guess. Yes?
With curves like upper degree polynomials, parabolas,
Polynomials is a cool idea. Polynomials are waves, bless you. But not waves like sines and cosines, and nobody wants to cover stuff with sines and cosines, okay? So that's definitely not gonna be an easy idea. But waves will work, because check this out. It would be nice to have some kind of just wave passing by, and then we know the area below the wave. That'll be awesome. So the idea of polynomials actually is used. We're using parabolas. Check this out. Why not to use parabolas, which is a quadratic function? Maybe concave down parabola, concave up parabola, concave down parabola, and then work with them. This is called Simpson's rule, because Simpson figured it out. So let's write it down. Simpson's rule. Simpson's rule uses parabolas, or basically quadratic, it's called quadratic approximation. Uses parabolas, and that's why it's called quadratic approximation. And this is very popular one. You will hear this name as Simpson's rule quite often in upper level classes and some engineering stuff. Formula for that, as sub n, because of Simpson, equals step size is delta x over 3 this time. All this is coming from the derivation, and it's in the book if you want to know. And now your job will be to memorize the formula. Okay, standing by itself, the first and the very last term. In general, the pattern of coefficients will be like so. It will be 1 standing by itself. Then it will be 4, 2, 4, 2, 4, 2. 4 have to be at the end. So you have to make sure that 4 standing on the edges like so. And then between them, it's 2, 4, 2, 4, 2. So 1 is at the edge. Plus, now as I told you, 4 should go after this. That will be f of x sub 1. Plus, now 2 comes into the picture. 2. F of x sub 2. Plus, and keep going. Plus, and keep going. Let's do 2. This is f x n minus 2. And here's a counter. It counts how many of them. N minus 2. Plus 4 n minus 1. We're getting to n slowly. And finally 1. The edge, x sub n, like so. This is the formula you'll have to memorize as well for the test. or at least know how to recognize it. So if I give you multiple choice, can you recognize it? The first thing is easy to see. It's over 3. Don't forget to do that. And then 1, 4, 2, 4, 2, 4, 2, 4, 1. But because of this pattern, Simpson's rule doesn't work for everything. It only works when number of n points is, and n should be even, so number of points should be odd. So only works, oh, I actually have this note here. Only works when n is even, so number of points is odd. Why is it so? Because, I wanted to say why is it even versus odd? We have number of points x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. How many points is that? 1, 2, 3, 4, 5, 6. If we have 6 points, how many intervals do we have? 1, 2, 3, 4, 5, 1 less. So this will not work. We will have to make sure we have even number of n intervals. So I will add 1 more, or basically divide by 1 more. And that will make the Simpson's rule work. So that's kind of how we're going to be looking for the approximations using 3 methods. And I did not give you formula for midpoint because it's here. So you will have all of them 3 written. Maybe write down this midpoint at the very end because I kind of skipped it to show you trapezoid and Simpson's. But all 3 are given in my notes. And you can always Google them. They're very famous methods. The thing is, there's a whole book or the whole area of mathematics called numerical approximation. And that's what people take in graduate school. We learn numerical approximation, numerical analysis. And people do a PhD in that. They do choose the problem to work on. Imagine if you work in microbiology as a mathematician, that's what we did, and you have cells. How would you approximate cells? There's also a different method to do that. And as you can see, ellipses will work, circles might work. Your imagination can go wild. And triangles was a pretty cool idea. Why not use triangles everywhere? See, triangles actually do work pretty good. So people will use those methods and they present the results in the conference, and you will see some people will raise hands and say, I can see you use numerical approximation. Which method did you use? And they will say, oh, I used this and that method. For example, Simpson's method. And you're educated enough now to know approximately what it means. You might not remember the formula, but you remember the idea, which is this. Trapezoid rule uses trapezoid, midpoint rule uses rectangle, and Simpson's rule uses Simpson's. That just makes sense. That's my favorite joke. Don't forget the donuts. Formulas for errors, I will explain it on Friday, but I wanted to show you this cool animation if it's gonna start. Ooh. Why you keep bothering me with this? Just give me the animation. What is your problem? Oh, it's getting somewhere. Yes, it didn't. Let's try again. Oh, it worked. Check this out. Using parabolas. Using parabolas makes it so good. Look how they're trying to match it well by tilting parabolas. Like there was mentioned right in class, it's using polynomials. And polynomials, they do tilt differently. X cubed has different behavior than x to the 5. The higher the power, the more it tilts and the more it wiggles also. So x to the 5 changes directions 5 times, up, down, up, down, up. X to the 4 changes direction 4 times, up, down, down. So the more you use, the more cooler approximation is going to be. So quadratic approximation was the first idea, and we will teach you with series and series expansions how to do it with upper level polynomials. But the idea is pretty cool that you can have concave down parabola, concave up parabola, to have this perfect approximation. And as you can see, they're approximating some kind of waves, and waves are everywhere. Sound waves and oscillators and wind waves and so on. So you will see that a lot in applications of mathematics, that they are using those methods And again, it's a last resort, which is recently the most popular one. When computers were created, computers now can calculate things numerically. And it will give you approximation to like 17th decimal point, and it's up to you to decide if it's good enough or not. Good job, people. Hope you liked the lecture.